Good afternoon, everyone. I'm Rochna Roshan, your webinar organizer from Center of Excellence on Watershed Management. Welcome to today's session on water resources management and challenges in India. To facilitate an uninterrupted session, please mute your microphones. If you have any questions, kindly type them in the chat box and we'll answer them at the conclusion of the presentation. Firstly, I would like to invite Dr. Dasok GS Sir, Consultant, Center of Excellence in Watershed Management, to welcome the speaker and the participants. Over to you, sir, please.
Thank you. Good afternoon, everyone. I am Dr. Dasok, Consultant at the Center here in Bangalore. It's my pleasure to welcome you all to our second webinar series, Hydrology Unplugged. Building on the success of our inaugural webinar series, Carbon Connect, which dwelt on soil organic carbon, saw over 1,800 participants. We are excited to shift our focus to hydrology, an important topic in the area of watershed management. We are honored to begin this series with a talk by our distinguished speaker, Professor Vijay P. Singh, Regent Professor, Distinguished Professor, and holder of the Caroline and William L. Lehrer Distinguished Chair in Water Engineering and at Texas A&M University, USA. Professor Singh is a global authority in water engineering, and his exemplary accomplishments and contributions to the field of water engineering are truly inspirational. My colleague Dr. Premanand will shortly provide a more detailed introduction of his illustrious career. On behalf of the University of Agricultural Sciences, Bangalore, the Watershed Development Department, Government of Karnataka, the Department of Land Resources, Government of India, the World Bank, and the Special Officer of the Center of Excellence on Watershed Management here, it is my privilege to warmly welcome you, sir, to deliver your talk on water resources management and challenges in India. I also would like to extend a warm welcome to the Vice Chancellor, officers, and faculty of the University of Agricultural Sciences, Bangalore, and other foreign universities in this country, and Karnataka in particular, the Commissioner and officers of the Watershed Development Department, Government of Karnataka, to Ms. Preeti Kumar, Task Team Leader and a team from the World Bank, the Secretary and officers of the Department of Land Resources, Government of India, as well as the National Rainfed Authority of India, scientists from ICR, IITs, and other esteemed institutions in India, officers from various development departments across Karnataka and India, and of course, dear participants who have joined and waiting for the lecture to begin. I once again extend a warm welcome to you, sir, and to all our esteemed attendees. Thank you.
Thank you, sir, for the insightful welcome address. Next, I would like to invite Dr. Premanand B.D., Professor, Department of Soil and Water Engineering, College of Agricultural Engineering, GKVK, Bangalore, and also in-house coordinator of COEWM, to introduce today's webinar speaker. Over to you, sir, please.
Okay, thank you. Good afternoon to everyone. I am Dr. Premanand Dashwant, Professor, Department of Soil Water Engineering, College of Agricultural Engineering, UAS GKVK, Bangalore. It is my proud privilege to introduce today's eminent speaker of the webinar, Professor Vijay P. Singh. He is a distinguished professor, Regents Professor, and inaugural holder of the Caroline and William N. Lehrer Distinguished Chair in Water Engineering at Texas A&M University. Coming to his academic qualifications, he received his BSc in Technology from GB Pant University, India, and then MS from Gulf University, Canada, and then PhD from Colorado State University from USA. And all his degrees are in engineering. He is a registered professional engineer, a registered professional hydrologist, board certified water resources engineer, and an honorary diplomat of European Water Resources Association. He is a member of National Academy of Engineering, that is NAE, and Academy of Georgia Physics Academy, a member of European Academy of Sciences and Arts, and a fellow member of 11 other international science and engineering academies. Then, coming to his membership to different associations, he is a member of American Society of Civil Engineers, an honorary distinguished member of International Water Resources Association, that is IWRA, and a distinguished fellow of Association of Global Groundwater Scientists, that is AGGS, and an honorary member of American Water Resources Association, and a fellow American Geophysical Union, a fellow of Environmental and Water Resources Institute, that is the EWRI, and then American Society of Civil Engineers, Indian Association of Hydrologists, ISAE, Indian Society of Agricultural Engineers, Indian Water Resources Society, that is IWRS, and Indian Association of Soil and Water Conservation. Then coming to his publications, he has published extensively in the areas of hydrology, irrigation engineering, hydraulics, groundwater, hydraulic geometry, water quality, food to water, energy, environment nexus, water resources, entropy theory, capillary theory, and climate change impacts with more than 1,615 refereed journals articles. More than 40 books he has published, 100 edited reference books, as well as Handbook of Applied Hydrology and Encyclopedia of Snow, Ice and Glaciers, and 130 book chapters and 330 conference papers he has already published. Let me tell about his Google Scholar citations are more than 1,13,695, H index of 140, and I-10 index of 1,283. He has received 4 honorary doctorate and more than 120 national and international awards. He has served as president of the American Society of Hydrology, that is AIH, president of American Academy of Water Resources Engineers, president of International Association for Water, Environment, Energy and Society, and chair of Watershed Council of American Society of Civil Engineers. He has served as editor-in-chief of 5 journals and 2 book series, and he has serves on editorial boards of more than 40 journals and 3 book series. He has given more than 190 keynote lectures and 300 invited seminars all over the world, and has organized more than 27 international conferences. Coming to the research.com, which is an educational platform, has ranked Professor Singh number 2 in hydrology in the world and number 13 among all the earth scientists in the world, whereas Scholar GPS has ranked him number 1 in hydrology and number 1 in drought in the world. He is not only an academician, but he is a great human. He is very kind, generous person. Actually, this information is not shared by VP Singh. Okay, personally, I want to tell his societal interest. In India, he is a native village near Agra. He established a school for imparting quality education virtually free of cost. And the school now has 4 campuses for graduated levels and a current enrollment of around 1,800 students. It is financed entirely through his own funds. In addition, he set up the foundation of aggrandizement of rural areas, that is FARA, advancing the cause of afforestation, civil hygiene, protection, management of water resources, and other issues, including women's emancipation. At the end, we are very proud to have you on this occasion of hydrology webinar series organized by Center of Excellence on Watershed Management, UAS GKVK, Bengaluru, Karnataka, India. Thank you, sir.
Thank you for an inspiring introduction, Dr. Premanand, sir. Professor Vijay Singh, sir, will now present on water resources management and challenges in India. Dear participants, please feel free to ask questions in the chat box, which will be addressed at the end of the session. Over to you, Dr. Vijay, sir, please.
Okay, first of all, thank you so much, Dr. Premanand Daswant, as well as the entire administration of Bangalore Agricultural University. I'm very glad to be invited, and I'm very thankful to Dr. Premanand Daswant for inviting me to speak to all of you today. So let's get started. And today we will discuss water resources management and challenges in India. And I have purposely avoided all the equations and graphs. So primarily the discussion will be more qualitative and in some ways a little more philosophical, because this topic is so very important. And this topic also is a very broad topic, which means that it is not only engineering and technological in nature, but also it encompasses many other disciplines, in particular the human dimension, which essentially relates to socio-political, economic aspects, but also ecological, environmental, and so on. So with that, let me, what we will do, okay. I think, okay. So we will first start out with discussing what the role of water is, and then we will move on to discussing what the sources of water are and where the water is being consumed. And then, of course, we will reflect on what the global water situation is and what is causing the current global water situation. And then we will essentially, that will take us to water resources management and what the challenges in managing water resources, especially in India are. And then I'll share with you my personal outlook and, of course, what I think the future outlook is. Okay, now, okay. Of course, we all know the water is the primary source of life, food and fiber, as well as energy, as you can see from the slide. But at times, water also brings misery. And this is what essentially the slide shows. Misery can be both because of lack of water as well as because of excessive availability or supply of water. Now, one of the minimum development goals of United Nations, primarily Millennium Development Goals, primarily or Sustainable Development Goals, is universal access to improved sources of drinking water and sanitation by 2025. If we really look at the current situation, then the ancient Romans had better water quality than half of the people alive now. This is quite amusing. Now, can you hear me well? Can everybody hear me well?
Yes, sir, we can hear you, sir.
Okay. Actually, the central role of water was enshrined in our scriptures. And as they say, Chit Jal Gagan Pavak Samira Panch Tatya Adham Sarira. I mean, people have been coining this central role of water in different garbs and guises. These days, people are talking about ecology, ecosystems, eco-hydrology. There are really different shades of the same coin that was propounded thousands of years ago in our country. And of course, this is also reflected in our rituals and traditions, particularly in rural India, where we start every ceremony, every religious tradition, every festival with fire, wood, soil, water, and plant leaves. Essentially, the same continuum that was formulated by our forebears thousands and thousands of years ago. And now, especially out in the West, people are claiming to have discovered the new concepts of eco-hydrology or ecosystems or ecology. But this thing was done by our forebears thousands of years ago. So role of water resources is also manifested by societal development, socio-economic development, industrial and energy development, ecosystem health and integrity, environmental management. Neither of these can be accomplished without water. So essentially, water, as we say, is vital not only for our survival, but also for all these developmental activities. Now, of course, if we look at the development or the drivers of economic development, which are education, communication, transportation, industry, agriculture, health services, governance, social fabric, cultural, religious, institutional, legal framework, environment, energy. These essentially drivers all depend on water, which means the central to the overall economic development is water resources. And if we look at the economic development of the nations across the world, we also observe that those nations which are managing their water resources or which have enough water resources are amongst the most developed nations. Now, we also recognize that water security is fundamental to life security, which is constituted by food security, energy security, environmental security, ecological security, health security. So, in other words, if we want to sustain and if we want to have life security, first we have to ensure water security. Water is also fundamental to health security, as we know that 80% of diseases in developing countries are due to the lack of access to clean potable water. Pathogens transmitted through water kill nearly 25 million people every year by amebia-linked diarrhea, cholera, and typhoid. And 98% of these people deaths occur in developing countries. Nearly 1,400 children under the age of 5 die every day, and 90% of these deaths of children under the age of 5 occur in developing countries. So, what this really says is the most effective management intervention is providing safe drinking water and proper disposal of human waste. We spend trillions of dollars on medical treatment, on hospital, and we forget that we can dramatically reduce medical costs, make lives a lot more comfortable, a lot easier, simply by providing safe drinking water. You don't have to really invest so much of money on maintaining health services if we can maintain safe drinking water access. So where are the sources of water? Obviously, the sources of water are surface water, water zone water, groundwater. In surface water, water is available in rivers, streams, creeks, brooks, and bayous, lakes, reservoirs, tanks, pools, lagoons, or in snowpacks in solid form or in glaciers. Now, of course, in water zone water, primarily it is the soil water, which is in unsaturated zone, and of course in groundwater, either through confined aquifers or unconfined aquifers. So where all this water that is available on the planet Earth is, now we know that approximately 2.5% of fresh water, which amounts to approximately 34 million cubic kilometers of water, is essentially fresh water. But the remainder, 97.5% of water, is essentially salt water, which is not usable for the most part. Of this 2.5%, now we find, or 34 million cubic kilometers of fresh water, only 0.1 million cubic kilometers of water is available or is found in lakes and rivers. Now, 10 million cubic kilometers of this fresh water is found as groundwater, and 0.3 million cubic kilometers of this fresh water is found as soil moisture. Now, look at here the irony. Only a small portion of fresh water is available in lakes and rivers, but that is where much of our attention has been as regards water resources management, and this is particularly true in our country, India. And if we look at little more detail, then we find that this 2.5% of fresh water, only 1.2% is of this 2.5%, only 1.2% is available in wetlands, large lakes, reservoirs, rivers, and other freshwater bodies. 30.1% is available as groundwater, and the remainder 68.7% is available in the form of glacier and permanent ice cap. So if you look at volumetrically, relatively speaking, there is a very small fraction of water, fresh water is available in lakes, reservoirs, where much of our water resources management and most of our water resources projects have been concentrated on. If you look at only, obviously, the water which is available in the solid form, in the form of glaciers and permanent ice cap, is beyond our reach. So that is, even though it's a fresh water, but we cannot really have access to it. So what we can access is water available on the surface and water available below the ground. But if we really look at it, you will find that almost, relatively speaking, almost all the fresh water is available in the form of groundwater, not in the form of the water that is available in the form of surface water constitutes a very small portion. Now, if we look at the glacier and permanent ice cap, and some decades ago, there was quite a bit of emphasis on transporting glacier ice marks to those areas, particularly in the Middle East, where they have a lot of oil and much less water. But of course, that is not really a practical alternative. But if we simply look at even this, the water that is available as glaciers or permanent ice cap, much of the water is available only in Antarctica. For example, in Asia, it's only 0.18% is available in the form of glaciers and permanent ice cap. In North America, only 0.27%. South America, 0.003%. In Australia, 0.0005%. In Africa, is less than 0.0001%. So that means much of this is available only in Antarctica. If we look at the groundwater, in Asia has 33.3% of groundwater. North America, 18.4%, South America, 12.8%, Africa, 23.5%. Australia has only 5.1%, very small, relatively speaking, amount of groundwater is available in Australia. Likewise, in Europe, only 6.8%. And if we look at wetlands, large lakes, reservoirs, and rivers, and where the total amount of water amounts to 124,200 cubic kilometers of water. But of this, in North America, 21.7%, South America, 25.8%, Africa, 25.6%. In Australia, it's very little, 0.002%. In Asia, 24.8%. So when it comes to fresh water that is available in large lakes, reservoirs, rivers, and so on, if you leave Australia aside, then Asia, Africa, South America, and North America have a relatively comparable fresh water. Now, this is interesting because the freshwater availability on a per person per year basis, according to United Nations, if the freshwater availability or access to per person per year is around 1,700 cubic meters, then of course we say that we are water secure or we have enough water. Between 1,500 and nearly around 1,100, we are still safe. We are doing all right, but not really, we don't have abundance of fresh water. The moment we goes below 1,100, then of course we are essentially in a serious situation. So water vulnerability situation. Below again, then it is water stress, and further below, it is water scarce situation. And if we go below 500 cubic meters per head per year, then of course it is absolute water scarcity. So where do we stand in India? In India, actually, we are in an underwater stress situation because the per head water available in India on an annual basis is less than 1,100 cubic meter. Now, so how much water do we have in India? If you look at the water balance for India, then average annual rainfall amounts to nearly 4,000 cubic kilometers. Now nearly 700 cubic kilometers is lost to atmosphere through evaporation and transpiration. Groundwater is approximately 2,140 cubic kilometers. Surface water is about half, 1,150 cubic kilometers. Total water sources available is 1,953 cubic kilometers. So the utilizable water is only 1,122 cubic kilometers. Now you divide it by nearly 1.5 billion population, you can easily see that we are underwater stress situation. So where all this water is being used, the water is being used for irrigation, for commercial purposes, livestock purposes, hydroelectric power generation, for mining activity, industrial activity, and energy generation, and of course for domestic use. Now, if we look at the water consumption on a global basis, then the water use has tripled since the 1960s. And what is interesting is the 5 major emerging economies, which we call as BRICS, Brazil, Russia, India, China, and South America, they use nearly 42% of global water over this period in the 50s. Now, developed countries like OECD, which is Organization for Economic Cooperation and Development, which has 38 members, they use 31% of global water, whereas the 5 BRICS countries use 42%. The rest of the countries, as you can see from here, the rest of the countries actually use much less. And this is largely because of the population. And if we look at water withdrawal, then we find, globally speaking, 68% of water is used for agriculture, 12% is used for domestic purposes, and 20% is used for industry and other purposes. And of this 20%, we find that 10% of water is used for power generation and 8% for essentially other industries. Now, if we look at Asia, then we find 81% of fresh water is used for agriculture, 1%. Only 10% is used for domestic purposes and 9% for industry. Whereas in North America, nearly 50% of water is used for energy generation, only 37% is used for agriculture, and 13% is used for industry, and 50% for domestic and other purposes. The same thing actually is pretty much true in Europe. And of course, the African situation is no better than our Asian situation, and which is not dramatically different from Latin American situation. Now, in domestic water, we find that a person really needs about 4 to 5 gallons per day to survive. Now, in rural India, which is really still true, people don't use a whole lot of water. Whereas an average American family, an individual uses at home nearly 100 to 176 gallons, whereas in Africa, an average family uses only about 5 gallons per day. In the Middle East, they're called MENA, that Middle Eastern and North African countries, which are in absolute water scarcity situation because the availability of fresh water is less than 500 cubic meters per person per year. Kuwait has the least water availability on a per capita basis. It was 27 cubic meters in 1970, 9 cubic meters in 2001. And it is projected to decrease to 5 cubic meters by the next year, 2025. And yet, Kuwait has the highest per capita water consumption. It was 200 liters per person per day in the 1980s, and now it is 500 liters per person per day. Now look at the irony. Kuwait hardly has any fresh water, and yet its freshwater consumption is among the highest in the world. So where this fresh water coming from? Primarily from desalination of Persian Gulf. And Persian Gulf is a very shallow gulf. It does not have a whole lot of water. Pretty soon they will run out of it. Anyway, if we look at globally, even in India, where, as I said, we don't have as much water, the consumption on a per capita, domestic consumption on a per capita per day basis is 100 to 150 liters. This is primarily because of overconsumption in the city, not in rural area. Now, of course, in Australia, which does not have a whole lot of water, the consumption is again 400 to 500 liters per person per day. Now, this is because the population of Australia is less than the greater Delhi area. The Australia is only about 30 million people. And so that I think is the reason why on a per capita basis their share is pretty high. In the United States, of course, it's more than 500 liters. Now, if we look at some major cities, which is again quite revealing. For example, if we take the case of Mexico City in Mexico, which houses nearly 21 million people in the metropolitan area, but the domestic water use is all the way up to 364 liters per person per day. And Mexico, for the most part, is an arid or semi-arid country. Buenos Aires in Argentina, which houses 12 million people in the metropolitan area, its domestic water use is 378 to 400 liters per person per day. But of course, in Argentina, they do have plenty of water. And Buenos Aires is situated along the banks of River Plata, which is almost like a flowing ocean. In Shanghai, 23 million inhabitants it has, and the domestic water use is 411 liters per person per day. China also is a little bit better than India, but not whole lot better. And yet their consumption in big cities is also among the highest. In New Delhi, we have 20 million inhabitants. Now, of course, now currently it might be a lot more than 20 million. And yet the domestic consumption is quite high, 78 liters per person per day. That was in 2007. Now it will be a lot more. This is quite interesting. If we look at the water consumption for agricultural production, now in general, nearly 1,000 liters of water is needed for growing 1 kg of grain. On the other hand, 15,500 liters of water is needed for producing 1 kg of beef. Now, if we look at, why our forebears emphasized vegetarian meals, or, for the most part, really, almost the entire country is vegetarian. Even those who eat meat, they eat meat only either as one part of their diet, but not the primary staple, not like European and American countries where beef or meat is the primary component of their everyday diet. But if we look at, for growing tea, we need 108 liters of water to grow 1 kg of tea. Tomatoes, 214, cabbage, 237, lettuce, 237, potatoes, 287, pear, 296, cucumber, 383, oranges, 560, and so on. But the interesting part is to grow 1 kg of chocolate, we need 17,196 liters of water. And yet the younger generation likes to have chocolate. Chocolate is the largest consumer of water amongst all agricultural products. Also the beef, you require 15,415 liters of water to produce 1 kg of beef. Pork also. And likewise, you have this, you can take a look at, and also let me also point out that anybody who is interested in having a PowerPoint, please ask Professor Dashavant, Premanand Dashavant. He will be happy to distribute the PowerPoint. So you don't need to make any notes, just listen to me, and then you can ask me whatever questions you have in mind on this topic as well as on any other topic. So if we look at now our daily diet, an average vegetarian diet costs only 2,000 liters of water, whereas meat diet costs 2.5 times more water, that is 5,000 liters of water. The problem with meat eating is, if we look at the case of China, in 1985, on a per head basis, China used only 20 kg of meat. And by 2009, it shot up to 50 kg. Now, by 2024, almost approaching 2025, it may be maybe 70 kg per head. But the problem is, even if you look at the figure of 2009, which is 50 kg per year, and given Chinese population, this is equivalent to 390 cubic kilometers of water, which equals the total water used in whole of Europe. The problem is, once you get used to a particular diet, it is very difficult to shift your dietary habit. That's where the danger is, even though these days there is a lot of emphasis in the United States and even in Europe on becoming vegetarian. But it is not easy to change your non-veg diets to vegetarian diet. Now, energy also uses huge amounts of water. Now, of course, the energy is also used not only for lighting our houses and generating electricity for industrial activities, but also energy is used for withdrawal, conveyance, treatment, and supply of water. In the United States, 116 billion pounds of carbon dioxide is produced while producing such energy, which is equivalent to pollution produced by 10 million cars. If we look at the water consumption for electricity generation, then we find the natural gas is the most water consumption efficient sector. It requires only 3 gallons of water to produce 1 million BTU if we use natural gas. In hydroelectric, we need only 20 gallons of water to produce 1 billion BTU. But in case of hydroelectric power, actually the water is not lost. It can be recirculated. So you can practically say that hydroelectric power generation is the most efficient generator of electricity. Fossil fuels, it requires 230 to 270. Coal, 41 to 464. Nuclear, 2,400 to 5,600. Ethanol, 2,500 to 29,100. Biodiesel, 14,000 to 75,000 gallons of water to produce the same amount of BTU, which is 1 million. Now, if we look at this, at least from a water resources viewpoint, we have to stay away from the production of electricity using ethanol or biodiesel, because these are not sustainable means of generating power. Now, of course, this is pretty much the same. Now, if we also look at how much water we were using, in 1950, 124 cubic meters per person. In 2021, it shot up to 149 cubic meters per person. There was a 23% rise. In energy intensity, it was only 13 million megawatts per person, 1965. By 2029, it shot up by 61% to 20.9 MWH per person. So we are using a lot of water. Again, as I said, if we look at the water stress situation, if we look at the water population, currently, today, nearly 2.3 billion people are living in very high stress, water stress area. And it is projected that more than half the world's population, so 4.1, more than 4 billion people will be living under water stress situation. Now look at the case of India. India is already under moderate water stress situation, almost all of the country. Now, those people who live in fancy areas in cities may not quite realize, but you go to rural areas. I come from a village near Agra, so I know exactly what is going on. And I do extensive traveling in rural India, and I find really there is not a whole lot of water. Millions of people from Rajasthan migrate from Rajasthan to UP in search of water because there is not enough of water. So we are already in a moderate water stress situation. So what is the current global water situation? We are witnessing the local water shortages are multiplying. This is quite true in rural India. current patterns of use and abuse, that is, the amount being withdrawn, are dangerously close to the limit and even beyond. The source to sea connections are severely interrupted. Only 37% of the global longest river remain free flowing. By longest river, I mean the rivers which have a length of at least 1,000 kilometers. An alarming number of rivers no longer reach the sea, and the examples are the Indus, the Rio Grande in the United States, the Colorado in the United States, the Murray-Darling in Australia, the Yellow River in China. And these major river basins are the arteries of main growing area, yet they never see the sea, the light of the sea. I have personally visited in the Indus near Hyderabad in Pakistan. I personally saw there was not a single drop of water downstream of the Kotra barrage. Not a single drop of water. And we are witnessing severe and long droughts in Australia, India, China, United States, Brazil, South America, you name it. And when the droughts are severe, more widespread, long lasting, then in the countries that heavily depend on hydroelectric power, say for example Sweden or Brazil, they will have difficulty generating enough power because there is not enough water to turn the turbines. So there are brownout. The other thing we also noticed that 68%, 68, not 68%, 68 largest aquifers of the world, which constitute 40% of all groundwater, has been extracted. One third of the aquifers have been depleted beyond recovery in human time. If we take the case of Ogallala Aquifer, which is one of the world's most important food-producing aquifers in the world, which is in the United States, which produces 1/6 of world's grain production, is in serious trouble. Why it is in serious trouble? Because, as they say, out of sight, out of mind, we don't see groundwater. But groundwater is being depleted at an alarming rate. So the imminent depletion of Ogallala and other aquifers around the world is a defining planetary crisis of our time. This is equally true in our country. Fortunately, in Indo-Gangetic Plain, many aquifers are unconfined aquifers. So they get recharged during the rainy season or during the monsoon season. And that is what is actually saving us in our country. Now, of course, in India, disaster has been brewing up for quite some time. Now it has started happening in India because we have a population of 1.45 billion, maybe actually more, and 0.3 million is likely to come. India is 1/5 of the global population, but only 4% of global water. India is the largest extractor of groundwater, 92% of which is used for agriculture. Now, two-thirds of the population depends on agriculture for their living. Tens of millions of farmers do not have enough water. And I can speak to it because I come from a farmer's family. Excuse me. My family still has a farm. Look at Delhi. Delhi faces a severe water crisis. As the Central Groundwater Development Board reports a significant decline in groundwater recharge and availability for extraction. This happened this summer, this year. In 2023, only 0.34 billion cubic meters of 0.38 billion cubic meters recharge groundwater was accessible, with 99.1% already extracted. Despite all efforts by the government, groundwater extraction rose from 98.16% in 2022 to 99.13% in 2023. I don't have the figures for 2024 because it is not yet over. While some areas have seen some improvement, but critical zones in the Delhi area were expanded to cover almost 35% of Delhi. So Central Groundwater Board is calling for urgent measures, including mandatory rainwater harvesting and enhanced groundwater production. This summer, this was the situation in Delhi. This is a photograph taken from Delhi. This is what is happening. The ladies were scrambling for getting water, which was being hauled to their areas through trucks. If this is the situation in Delhi, you can imagine what the situation will be like in rural areas where there is very little attention being paid by the government. Nearly 1 billion people, that is 1 in every 7 people across the world, do not have access to safe drinking water. And it is expected that almost 2 out of 3 people on this planet will be living under water stress situation by the year 2025. Now, of course, this is, India, as we have already said, nearly 54% of India faces high to extremely high water stress situation, as you can see from this figure. 54% of India's groundwater wells are decreasing. In China, the situation is not all that great, all that better. More than 50,000 rivers have been actually have disappeared. And, their environmental minister gave an offer to the head of the department, the local environmental protection of 32,000 for 20 minutes swim, which he refused because there is not enough water. Now, of course, the same thing is true with Iran. It is even worse in South Africa, likewise in the whole of African continent and in Australia. This is, in other words, there is a lot of water stress spread all over the globe. Now, why it is happening? But before we do that, that is water resources management, take the case of Lake Chad, one of the largest freshwater lakes in Africa. In 1963, Lake Chad occupies part of the territories of 4 nations, Chad, Cameroon, Nigeria, and Niger. By 2087, basically is occupied only a small portion of Chad, a small portion of Cameroon, and a small portion of Nigeria, but no portion of Niger. By year 2007, it pretty much disappeared except for a small area in Chad. If you look at Aral Sea in the former Soviet Union, now of course part of Kazakhstan, now you will see the Aral Sea in 2000 had plenty of fresh water. By the year 2018, it's pretty much disappeared entirely because of mismanagement. Because the river that was feeding the sea to sustain the sea life or the life of the sea essentially was diverted to grow cotton in Kazakhstan and Uzbekistan. So the net result is the sea had pretty much died. In California, you see Lake Folsom and Lake Oroville, 2 of the largest lakes. In 2011, within a period of just 5 years, in 2011, you don't see the date here, the Folsom Lake has reduced to a very small size. Oroville Lake pretty much disappeared except the rivers within just a short period of 5 years. And Lake Mead, which is one of the largest freshwater lakes behind Lake Mead, which is considered to be an engineering marvel. This is what has happened. The water level has declined by more than 30 meters. In fact, there is not a whole lot of water left in Lake Mead. And 2 cities, Las Vegas and city of Los Angeles, depend on the fresh water. This is what the situation is. The same thing has happened to Lake Poyang in China. In 2011, it was a fresh, pristine lake. By 2022, it has pretty much disappeared within a period of 22 years. So what is causing all this? Primarily, 80% of this water scarcity is attributable to population rise. But also, population rise has other implications. Higher food and energy requirement, which lead to higher water requirement. Also, economic development, changing habits from vegetarian to more water consuming diet. In the last 50 years, we know the population has increased from 3.7 billion to 7.7 billion, and water use has increased from 2,360 cubic kilometers to 4,600 cubic kilometers. Now, the projections are that population is going to increase by another 1.7 to 2.5 billion, depending upon which projection you believe in. The water use will increase another by 20 to 30% above the current level. More than 50% of the people will be living under water stress situation which means or water scarce situation, which means nearly 6 billion people. And of course, this you can see it, so I think I will not go over this. Now, the other thing is the world is urbanizing rapidly. By 2050, 70% of the world's population will live in urban area. 94% of this increase, of the 70%, will actually happen in low to middle income countries, including India. Now, this enormous migration from rural areas to urban areas is resulting in expansion of slums. Also, another serious implication is that the infrastructure is not able to keep up with this fast pace of expansion. Now, the government can only do so much. People also have to start taking responsibility. So, what can we do? The only option that we have to overcome the water scarcity situation or water stress situation, or at least to reduce it, is water resources management. We don't have any other option. The management, when we talk about it, essentially is comprised of two components: scientific management and non-scientific management. Scientific management entails hydrologic, hydraulic, environmental, and ecological, climatic, agricultural, all branches of science that bear on water resources management. Non-scientific management is also equally important. And I want to stress this: non-scientific management can also be considered as a human management, because this includes economic, social, political, cultural, judicial, administrative, and public party. You can have many other dimensions, but the non-scientific management is just as important as the scientific management. Until the decade of the 60s and so, the main emphasis in water resources management was primarily on scientific management, which means only two things: engineering soundness of a project and economic viability. Most of the other factors, to some extent, were taken into consideration, but they were not really given as much importance. But now, it is not the scientific management, it is the non-scientific management that is becoming a lot more important, because the scientific management will not be successful unless we provide or we do proper non-scientific management. Now, where all this management comes into picture, from my point of view, management starts right from the beginning, which means planning, design, development, and construction, operation, utilization, maintenance, repair, conservation, administration, law, public relations, sustainability. So the management encompasses pretty much every facet of water resources project, which is almost like a human life, every facet. And that's the only way we can have. So that means we have to have integrated water resources management, which in the area of scientific management will entail simultaneous consideration of surface water, groundwater, quantity as well as quality, watershed as well as water body, which will involve hydrology, hydraulics, environment, policy, and socio-economic. That will involve multiple sectors, multiple stakeholders, multiple decision makers, and multiple players. Engineers and scientists cannot solve the problem. Administrators alone also cannot do sustainable water resources management. Water resources management has to be done in a comprehensive, integrated manner. So that means in order to have a sustainable management, we will have to combine both scientific and non-scientific management component. Scientific management will have to start with the data gathering and processing, modeling, verification, risk and reliability, uncertainty analysis, implementation, also learning from experience. And it will also have to depend on public or stakeholder participation. Otherwise, we will not have a sustainable management. So how can we accomplish all this? Fortunately, we do have tools for water resources systems analysis and decision making. We have mechanistic tools, we have data mining tools, we have tools for doing uncertainty analysis, such as entropy theory, risk analysis. We have tools for doing multivariate analysis, which becomes quite important, especially in this era of global warming and climate change. Things are not in engineering arena the way they were 50 years ago before we recognized that climate change was looming on the horizon. We do have optimization algorithm. We have decision support system. We have tools like geographical information system. We have tools like data collection, data mining, data collection through satellites and remote sensing technology. Now we have to recognize that we have to employ these emerging technologies because water is limited and it should not be wasted. It has to be conserved. Every drop conserved is a drop that can be used for other purposes. Now, this is particularly true and must be emphasized in the area of irrigation, which uses the lion's share of fresh water. So irrigation has to be more efficient. If we can make irrigation even 10% more efficient, this 10% saving of irrigation water will go a long way to address water shortages and water scarcity in all other areas, because that will amount to huge volumes of water saving. Now, of course, we cannot make irrigation efficient simply by making irrigation technology more efficient. It will also require participation from agricultural scientists, particularly economists, crop breeders, because they have to determine crop water need, crop area, crop type, soil type, climate, irrigation methods. And all these disciplines will have to be brought together to bear on making irrigation more efficient. And of course, we'll have to have water treatment. We will have to expand water supply, which means water supply will have to have more diversified portfolios. If new surface and groundwater resources are available, they will need to be developed. But more importantly, better management will have to be implemented. Now, unfortunately, because of global warming and climate change, sea level rise is occurring. We will have to arrest sea level rise because sea level rise contaminates coastal aquifers. Global warming and climate change is also increasing the size and intensity of storm water. And that again affects sea level rise and in turn coastal aquifer contamination. The sea level rise may affect the design and performance of coastal and estuary structures as well as habitat. Planning for new projects will have to include the impacts of climate change and global warming. Existing infrastructure facilities were designed using hydrologic records that did not reflect the effect of climate change. So they will have to undergo systematic revision. In other words, all the existing infrastructure will have to go systematic revision. Now that poses a lot of challenges. So the challenges are first with respect to the water availability. Do we have enough water to all the people at all places, at all times, at affordable cost? Obviously, we don't. Also, there are challenges with regard to water quality because adequate quality of water to all people at all times at affordable cost, which we obviously do not have. Now, how can we meet this challenge, or can we meet, or are we doing enough to meet the challenge? Now, of course, the answer is partly yes and partly no. For the most part, actually, the answer is no. the factors which are compounding the challenge, particularly water quantity and water quality crisis, is increasing population. How can we arrest increased population or arrest the increase in population? Also, increasing urbanization, which leads to massive land use change and significant deforestation. Also, our standard of living is rising. Increasing demand for water is increasing, demand for irrigation is increasing, demand for industrial activity is increasing. And all these are leading to environmental degradation, higher use of chemicals, increasing land use change, increasing fertilizer application, increasing industrial activity, increasing oil and gas production, increasing automobile activity. And there are other factors which are actually compounding the challenge. Other factors are obviously climate change. Many river systems in our country are at risk, including the most sacred, the most pious of all the rivers on the planet is our Ganga River. In English, they call Ganges. I don't like the word Ganges because it should be Ganga. But anyway, the Ganga River is also in peril despite the expenditure of lakhs of crores of rupees over the past 3 or 4 decades. Still, it is not in good condition. It's terrible. All that you have to do is just look at the Ganges water at different places. Now, there is so much of misuse and destruction of rivers going on, especially small rivers. Nobody seems to care. In my own village, near my own village, there are 2 rivers. They have pretty much died. They used to be, I remember very vividly, when I was growing up in the 50s, they were freely flowing rivers throughout the year. Now, so they first became ephemeral, then they became intermittent, then they become ephemeral. Now they are pretty much deceptive. For the most part, they have died. There is an enormous thirst for energy which is demanded by our current lifestyle. The question is our civilization at risk? Probably. So we have to assess how much water do we have or how much is the water availability. Now, that will have to be done with the beginning of measurement. Measurements of hydrologic, hydrometeorologic, hydraulic, environmental, and agricultural variables. Now, of course, in our country, fortunately, we do have enough measurements of some hydrologic variables, particularly precipitation, especially rainfall, and other hydrometeorologic variables, as well as stream flow, but not others. For example, we don't have enough records of groundwater. We have virtually no records of surface soil water. We have very little records of snow cover. We have very little records of geologic formation properties or hydrogeologic parameter. Very little records of environmental health, ecological health, and integrity. Now, of course, whatever measurements we have, these measurements have to undergo processing, archiving, and retrieval. These measurements should be freely accessible, which is not the case in our country, unlike the United States, where anybody sitting anywhere in the world can have access to all these measurements or all the data supported by public exchequer. Now, fortunately, we do have modern measurement tools, remote sensing, isotopes, tracer, and of course, we have new modeling tools and resources. So the challenges in the assessment actually pertain to data availability. We have to have a central archiving. All the data should be, especially funded by the government exchequer or the government funds, must be within public domain. In other words, they should be freely available to the public. Each data set has to be subjected to quality assessment and quality control. And there must be proper coordination amongst data collection agencies. We do have tools and techniques for data processing. We can assess errors. We can assess consistency of data. there must be compatibility between data type and modeling needs. And there should be proper training of data collection personnel, and there should be automation. Unfortunately, in our country, the people who do kind of menial job, so-called menial job, in other words, the people who are doing data collection are not as highly paid because their job is not considered as sophisticated or as technical. So the net is the person who is collecting the data does not know what he's collecting the data for, or he has very little appreciation for the work that he's doing. He does not take pride in the work that he's doing. That is not the case in the United States. And unless we change our mentality of going out of this hierarchy of classification and respecting only those people who occupy high position and paying them very well, and not respecting those people who occupy an Indian hierarchical system, lower position, and not respecting as much, will lead to essentially this very grievous situation. Now, obviously, we have a growing water use. This is another challenge. Now, of course, how can we arrest? This is a challenge. How can we arrest the population? A vast majority of problems can be addressed, will automatically disappear if we have a control on the population. If India had a population of, let's say, 200 million people, I can guarantee India will be more prosperous than the United States or any other country. The problem is this enormous population. The government is trying very hard to provide the facility. By the time the infrastructure is developed, the population outpaces the infrastructure. It is very difficult, and this situation is going to get worse down the year. Now, of course, as I said right in the beginning, there is a very strong linkage between food, energy, environment, human health, and water. Now, 1 calorie of food requires 1 liter of water to produce it. Now, Western diets normally have 2,500 to 3,000 liters of water per day. And by 2030, additional 2.5 billion people will be added. So meaning that will require another 2,000 cubic kilometers of fresh water to feed the growing population. Now, there is growing urbanization, which is putting agriculture in further stress. And there is a gap which is increasing the gap between demand and supply. Now, why the question always arises, why people have to move from rural areas to urban area? Of course, we all know the answer, because the rural areas have long been neglected. There are no employment opportunity. There are virtually no educational opportunity, not like the United States, where they started establishing universities in the rural areas under the Land Grant Act. Just like the only exception I see in India is the GB, University of Agriculture and Technology. I got my bachelor's degree in engineering from that university. That's the only school that was established in the middle of the farmland. Otherwise, all agricultural universities that I know of have been established in the middle of major cities. I don't understand how can you establish an agricultural university in the middle of a major city. Look at Madhya Pradesh, look at Rajasthan, look at Punjab, look at Haryana, look at Tamil Nadu. You look at Bangalore, Bangalore Agricultural University. In Bangalore, I don't understand this logic of administration anyway. Then the other factor which is compounding the challenge of meeting and doing integrated water resources management is climate change. And I will not really go over, I will only say this, the climate change is impacting almost every aspect of our life, particularly in the water area. It is impacting the hydrologic cycle. It is intensifying the hydrologic cycle, which is changing the precipitation regime, which is changing the evapotranspiration regime, which is making the glaciers and ice and snow masses melt early, which is reducing the snowfall season, which is increasing the frequency and intensity of extreme weather events. It is decreasing crop yields because the cropping patterns are not are changing, but they are not keeping pace with the climate change. Look at this area. In my own area in Agra, in my village, there has been very high rainfall that occurred very untimely, which pretty much destroyed my entire area, the Kharif crop. Pretty much destroyed. Not only that, the late rainfall was so heavy that much of the land still is not ripe for cultivation. So that means not only they lost for Kharif crop, but some farmers are also going to be losing or will be having reduced Rabi crop yields because of late sowing. This is what is happening. And so it's changing everything, and I'm not really go over all this. But I would like to emphasize this. If we look at the drought, there were 10 droughts in a period of 20 years, beginning with 1996 and through 2015. The climate change is expected to increase the frequency and the magnitude of this extreme weather event. In this period, 10 million people were affected annually, and 1.1 billion people actually were affected in total, and 22,000 people or more were killed. And these droughts caused more than 100 billion US dollar within a period of 20 years. More than one. That means $5 billion on average per year. If we look at the flood events during the same time period, from 1996 to 2015, 100 flood events occurred. The people at risk were in 2010, 1.2 billion. It is expected by the 2050, the number of people who will be affected by flood events will rise to 1.6 billion, which will amount to nearly 20% of the world population. Nearly 35 million on an annual basis were impacted by flood event during this period. Likewise, the climate change and global warming is impacting coastal flooding and sea level rise. So an increase of, it is expected that there will be an increase of nearly 48% of the world's area, and 52% of the population will be impacted by coastal flooding and sea level rise by the turn or by the end of this century. And it is projected that 68% will be due to tidal and storm event, and 32% due to seasonal sea level rise. So the people going to be affected by rising sea level, in 2009, they were affected 110 million, by the end of this century, 190 million people in low emission, according to low emission scenario, and 630 according to high emission scenario. That's a lot of people. 50% of the droughts are associated with El Nino, and there will be consecutive droughts and cyclones. So let me not go over. And this is going to impact the monsoon season in India, on which we so heavily depend upon, because there will be uneven distribution of rainfall. 20% rise in all summer monsoon rainfall. So the climate change will make monsoon more unpredictable, and that will accentuate extremes, severe drought, severe flooding. And El Nino can also delay and cause the monsoon to fail. So what is the future outlook? Future outlook is, actually in the water resources area, we need more model. This is a challenge. We will need more data at finer spatial scale. We'll have to undertake regional scale model, uncertainty analysis, and we will have to have long-term forecasting, particularly for probable maximum precipitation and probable maximum flood. We will have to integrate water resources models with biogeochemical model, and they will have to be integrated with climate models as well as ecosystems model. And then they will have to be coupled with the decision-making issues, social, political, economic, environmental, judicial, administrative, all the. In the water resources area, when it comes to modeling, the models will have to be user-friendly. we'll have to provide model choices and enumerate model credibility, which means we'll have to scope out our entire environmental and water resources field. So where do we go from here? We will have to re-examine our entire water, energy, soil security system. But that will involve a very close partnership amongst academia, government sector, NGOs, in the private sector. We cannot operate anymore in isolated silos. There will have to be close partnership. And the reason is very simple. We are all trying to achieve the same end, but we have a difficulty combining our approaches, combining our effort, doubling our energies, and going hand in hand toward achieving the goal. Now, that will have to start with our educational system. Unfortunately, our educational system is pretty much outdated as far as I'm making a very bold statement, but this is really true. Remember, our educational systems were devised centuries ago, even in engineering. Our curricula were devised 50, 60, 70, 80 years ago. This is because the problems were different based on our desire to address those problems. We divided engineering discipline into different sub-disciplines. But unfortunately, we created boundaries, rigid boundaries. Now we are having difficulty crossing those boundaries, even though I must reckon that engineering curricula are undergoing revision on a frequent basis. But the revisions have been relatively minor. The revisions have not kept pace with the changing needs, the changing technology, which means we will have to train the trainers and teach the teachers. And that will require innovative, revolutionary, and self-sustaining programs, which will also involve diverse and multi-institutional partnerships. Water will no longer have to be free or very cheap. There will have to be evaluation and pricing of water if we want to enhance water use efficiency. And that will involve strong integrated planning for water, soil, energy, and agriculture, and which will depend upon robust regional capacity building. So our entire development paradigm will have to change. So what is our development paradigm? If you look at everywhere, particularly in India, where are our developments occurring? Developments are occurring primarily in cities where a small number of people live. Look at all educational institutions. Where are they? Only in big cities. They have completely ignored the vast number of people living in rural areas. More than 65% of population lives in rural area. Can anybody tell me where IITs are located, where central universities are located, where medical schools are located, where agricultural universities are located, where technical institutions are located? Our development is primarily what I call point development. The development will have to be distributed. If we do that, I don't think people from rural areas will like to move to Delhi. Nobody will like to move to Delhi. The people like to move to Delhi only because there are facilities over there. Or from my area, they will like to go to Agra only because in Agra, they have some facilities, whereas in my village, the facilities are none. So obviously, where will people go? The current generation will like to go to urban areas where there are facilities. If you make facilities available, if you make development, employment opportunities available in rural areas or sparsely populated area, people will not move. So we will have to change our entire development paradigm if we want to be a sustainable society. So that means we should really sit down, sit back, take a stock of the current situation, recognize our social and cultural constraints, and take account of looming global changes, not only in terms of religious and cultural and demographic landscape, but also in terms of IT. technology, we'll have to also re-examine and re-evaluate our social values and value system. The future can be bright or dark. It's all in our hand. It's up to us. And with that, I will only say natural resources, including water, are God's gift. We must use them wisely because we owe it to our future generations that we leave them in a better shape than the shape we got them in. So, with that, let me thank you. And I would be very happy to answer any questions that any of the participants might have.
Sure, sir. Thank you, Professor Vijay Singh, sir, for the enlightening presentation on water resources management and challenges in India. Your expertise and insights on this critical topic are truly invaluable and timely. Thank you for sharing your knowledge with us. Now I request Dr. Lakshminarayan SV to facilitate question and answer session, addressing questions from the chat box. Please proceed, sir.
Good afternoon, sir. A few questions arise from participants. I'm asking
Yes.
questions. Question number one is, there are a lot of groundwater recharge projects happening in India. Will they make any difference to set 1/3 aquifers that are behind recovery?
I think you have either you or whoever has raised the question is exactly the point I was trying to make. There is no dearth of technology. The problem is one of management. We are a society where we spend a lot more time arguing, and arguing. Whether you take the case of politics or the case of any other sector. We don't spend as much time on coming together and addressing the problems at the grassroots level. The problem is we have to use natural resources very wisely. The problem in India is much of the government emphasis in water resources sector has been on the development of surface water resources, construction of dams, river control, and so on. But there is hardly any emphasis on the development of groundwater resources. For example, there is absolutely no law as far as I can think of, because in my area, on my own farm, my family has 7 farmers, 7 different places. They just, we just construct the tube and withdraw the water as much as we can. On my own school, which I established in 1994, first we established a tube. That water table was only about 6-7 meters below the ground. A few years later, the water table went down to about 15-16 meters. So we had to construct another tube. 10 years later, the water table went down more than 30 meters. So we had to construct a tube well to access the water from the depth of more than 30 meters.
Separately to all the audience, I am seeing as many as 300 participants from the beginning till end. They're all listening to your lecture. So it is
Okay,
very informative and really
please come in.
great to hear about you the entire water resources in Indian context.
No,
So,
thank you.
Thank you very much, sir. Thank you very much. Please do visit our center during your next visit to India.
I visited your center. I think
Yes, sir. Once
Premanand invited me. It was very kind of him. And I did visit, I think that was 2 years ago, if I'm
Sure,
not
sir.
mistaken. And I very much enjoyed staying in the university guest house. The vice chancellor was very kind. All the faculty members were very affectionate, very kind to me. And my visit was very enjoyable. And, if of course, as I said, I come to India quite frequently, but whenever I come, my program gets filled up before I even step foot in India. So if Premanand asked me ahead of time, then perhaps I will try to make time. You never find time. You have to make time.
Sure.
And which is what I very strongly believe in, that if you think anything is important, you will have to create time for it. Because all of us, I'm no exception. You just don't have enough time anyway. Nobody has enough time because we have more activities than we have time for. But we do have the ability to create time for what we think is important. So let Premanand contact me ahead of time. And Bangalore is one of my favorite cities. So I would be very happy to visit. Thank you so much.
Yes, Rochana, please.
Yes, sir. Thank you, sir. Finally, I would like to invite Dr. Virupaksha HS to deliver the vote of thanks.
Good afternoon. So I would like to extend my heartfelt thanks to our esteemed speaker, Professor Vijay P. Singh, for the insightful and engaging presentation on the topic Water Resources Management and Challenges in India. I would also like to thank the Commissioner, Watershed Development Department, and the Special Officer, Center of Excellence on Watershed Management for their valuable support and encouragement. Special thanks to Professor Premanand for introducing the speaker. Finally, I express my sincere gratitude to the participants from diverse specialization who have joined us. Your participation and engagement made this event a resounding success. We hope the session provided you with valuable insights, and we look forward to welcoming you to our future webinar
Thank you,
events.
Virupaksha, sir, and thank you everyone for your active participation in today's webinar. As we bring our session to an end, let's take a look at what's on the horizon. With today's webinar, we have embarked on theme 2, that is Hydrology Unplugged, exploring the fascinating world of hydrology, uncovering its significance, wherein we will be exploring other 3 captivating subtopics over the next 3 months. Join us as we venture into continuing this new territory each month. This new theme follows the successful completion of our first webinar series focused on soil organic carbon over the past 4 months. We are delighted to have shared that journey with you and are grateful for your enthusiastic participation and ongoing support, and look forward to your continued participation. Thank you, and we'll see you at our next webinar next month.
Thank you, sir.
Thank you,
Thank you,
sir.
sir.
Okay.
Thank you. Thank you, sir.
Thank
Thank
you.
you.